Openstax College Algebra. In this video, I'm going to cover the Openstax College Algebra textbook, which you can download for free at openstax.org. And I'll be talking about Chapter 1.2, Exponents and Scientific Notation. Proxima Centauri, the nearest star to us, is 40 trillion kilometers away, or 25 trillion miles. It's 4.25 light years away. Light years are a measure of distance, and this is a huge number. It's also possible to have very, very tiny numbers. The diameter of a hydrogen atom is roughly 4 billionths of an inch, a very small number. We will learn how to represent very large and very small numbers, as well as we'll learn the rules of exponents. Let's consider the product of x cubed multiplied by x to the power 4. So x cubed has 3 factors of x, and x to the power 4 has 4 factors of x. That gives us 7 factors of x. So we see that x cubed multiplied by x to the power 4 is equal to x to the power 7. So this suggests the product rule of exponents. For any real number a and natural numbers m and n, a to the power m multiplied by a to the power n is equal to a to the m plus n, the product rule. Example 1 asks us to use the product rule. So for part A, I have t to the power 5 multiplied by t to the power 3, and I just add the exponents. So this is going to give me t to the power 8. Notice it says, write each of the following products with a single base, don't simplify. So I just need a single base. Part B, the base is negative 3 to the power 5 multiplied by base negative 3, and there's nothing written there, so I know that the exponent there would be a 1. So that means the base is negative 3 to the power 6. And it says don't simplify further, so I can leave it like that, even though I could actually calculate a number there. Next I have x squared times x to the power 5 times x cubed. And the base here is x, and I've got to add everything together. So I'm going to write an intermediary step in here. It's going to be 2 plus 5 plus 3 in the exponent. So this result will be x to the power 10. Now we're going to think about the quotient rule. So let's suppose that we have y to the power 9 divided by y to the power 5. So there are 9 factors in the numerator and there are 5 factors in the denominator. So if I cross out y divided by y, because that's just 1, and I do that, and it turns out that I'm going to have y with 4 factors all over 1. So that's going to be y to the power 4. So this suggests the quotient rule for exponents. If I have a real number a, which is the base, and natural numbers m and n, where m is greater than n, then the quotient rule of exponents states a to the power m divided by a to the power n equals a to the exponent m minus n. Example 2, we're going to use the quotient rule, and we're asked to write the products with a single base and not to simplify. So in part A, the base is negative 2 to the power 14 all over base of negative 2 to the power 9, and because it's a quotient, the base is going to be negative 2, and I'm going to write the intermediate step in here, which we'd normally do mentally. So the exponent would be 14 minus 9, so that would be negative 2 to the power 5. So in part B, we have t to the power 23 divided by t to the power 15. So that equals the base of t, 23 minus 15, which is t to the power 8. And in part C, the base is z times the square root of 2 all to the power 5 all over the same base, z times the square root of 2. It doesn't tell us a base here, but when there's no base, we know there's an understood base of 1. So this means the base is z times the square root of 2, 5 subtract 1, which is 4. Now we'll talk about the power rule of exponents. And that happens if we have an exponential expression raised to some power. In this case, we have x squared, our exponential expression, raised to the power 3. So that means we have x squared times x squared times x squared. And of course that's going to be x times x times x times x times x, or x to that. There's 6 factors here, isn't there? X to the power 6. So this suggests the power rule of exponents. And that means for any real number a is the base, we have positive integers m and n. If we have a to the power m, our exponential expression, all raised to the power n, then this is a to the power m times n. In example 3, we're really asked to just apply the power rule. And it says write each of the products with a single base, don't simplify, you're just applying the power rule here. So here I have x to the power 2 all to the power 7, so that is x all to the power 2 multiplied by 7 in the exponent, so that leaves me with x to the power 14. For part B, I have 2t is the base to the power 5, and then I'm going to raise that expression to the power 3. So the base here is 2t, and the exponent will be 5 times 3. So I have 2t to the power 15. In part C, I have a negative 3 to the power 5, and I'm going to raise that exponential expression to the power 11. So the base is negative 3, and the exponents are 5 multiplied by 11. So here I have base negative 3 to the power 55. And I don't need to simplify it further because that's what it says. Now we're going to talk about the zero exponent rule, and for that we'll need to remember the quotient rule. So if we have t to the power 8 all divided by t to the power 8, well, that obviously cancels out to be 1, doesn't it? But if we also remember the quotient rule, t to the power 8 divided by t to the power 8, well, we had said in the quotient rule that m had to be greater than n. But if we say 8t to the power 8 subtract 8, we get t to the power 0. So that suggests the zero exponent rule for any non-zero real number a, that's the base, a to the power 0 equals 1. In example 4, we're going to use the zero exponent rule. So a is pretty straightforward. We have c to the power 3 divided by c to the power 3. So that means we would be thinking, okay, the zero exponent rule is c to the power 3 minus 3, c to the power 0, and I know that is 1. Now, on part B, it's a little bit more complicated. I have minus 3, x to the power 5, all over x to the power 5. Now, I could just cancel here, but it says use the zero exponent rule. So this actually becomes negative 3 times x to the power 5 all over x to the power 5. So I have negative 3 times x to the 5, subtract 5 in the exponent. That's negative 3 times 1, or negative 3. Part C is going to require me to do a little bit more work too. So here the base is j squared times k. That's the base. And in the numerator, it's to the power 4. In the denominator, we're going to have a little bit more work to do. So we have j squared times k multiplied by the base of j squared times k to the power 3. So this, once we do a little work, remember, of course, we don't see an exponent here, but we know the understood exponent is 1. So in the numerator, we have j squared k to the power 4. And in the denominator, we're going to have to use the product rule. So we have j squared to the power k, and using the product rule, that's going to be 1 times 3 in the exponent. So we're going to end up with the base of j squared k to the power 4 in the numerator, also in the denominator. And now we can apply the power rule. So j squared k is the base to the power 4 minus 4. And that's going to be j squared k to the power 0. And that equals 1. Part D is very much like B. So I have 5. The base here is rs squared, all squared, and in the denominator I have the base of rs squared to the power 2 again, and that is just like 5 times rs squared squared all over rs squared squared. So that gives me 5 multiplied by the base of rs squared 2 minus 2. 5 times rs squared to the power 0, 5 times 1, which of course is just 5. Next, we're going to talk about the negative rule of exponents. So we're going to relax the condition even more that m has to be greater than m and just say it can be anything. So let's consider our example here. H cubed divided by h to the power 5. And you can see here, if we write out the factors, we end up with 1 over h squared. And this suggests the quotient rule still applies. So 3 minus 5 would give us h to the minus 2, but we already know that h to the minus 2 in this case has to equal 1 over h squared. So the negative rule of exponents would be a to the minus n is equal to 1 over a to the n. Now in example 5, we're going to use the negative rule and write your answers with positive exponents. So in part A, we have theta cubed all over theta to the power 10, and by our quotient rule, that's theta to the 3 minus 10, or theta to the negative 7, and of course, writing it with a positive exponent, that's 1 over theta to the power 7. Now in part B, we have z squared times z all over z to the power 4. So that's actually going to be z cubed in the numerator and z to the power 4 in the denominator. So that's z to the 3 minus 4. Because this step here we often do mentally, but because this is the first time I'm telling you about it, I want to write it in. So that is z to the power negative 1, or 1 over z. And of course there's an understood exponent of 1 there, but we don't normally write that if the exponent is 1. In part C, we have the base of negative 5t cubed all to the power 4 all over negative 5t cubed to the power 8. So we know the base is negative 5t cubed 4 minus 8. So negative 5t cubed all to the power negative 4. So that is 1 all over negative 5t cubed all to the power 4. In example 6, we're kind of going to use mostly the product and quotient rule, but we might have to use some other rules as well. So in part A, I have b squared multiplied by b to the minus 8. And the product rule here tells me this is b, and it's 2 plus negative 8, isn't it? So I'm going to have b to the power negative 6, which just is 1 over b to the power 6. In part B, I have minus x with the exponent of 5 multiplied by minus x, the base negative 5. And here I have the base of negative x. And of course this is 5 plus negative 5 by the product rule, or the base of negative x to the power 0, and that's just 1. In part C, negative 7z all over negative 7z to the power 5. The understood power in the numerator, of course, is 1. So the base is negative 7z, and I have 1 subtract 5, or negative 7z to the power negative 4, and that's 1 over negative 7z to the power 4. Now we'll talk about finding the power of a product. To simplify the power of a product of two exponential expressions, we will use the power of a product rule of exponents. So here we have PQ as a base cubed. Of course, that's PQ times PQ times PQ. And that gives me 3 factors of P. So it's P cubed times Q cubed. And that suggests this power of a product rule of exponents. The base is AB to the power n, and that's going to be A to the power n times B to the power n. So in example 7, we're going to apply the power of products rule, and we're asked to simplify each of the following products as much as possible by using the rule and writing your answers with positive exponents. So part A is AB squared cubed, so that's going to be A cubed times B squared cubed, and then we might do this part mentally after a while. So that's A cubed times B to the power 2 times 3. We might do that part mentally after a while. That's the product rule. So we have A cubed B to the power 6. Now in part B, now we have 2t to the power 15. So that's 2 to the power 15 multiplied by t to the power 15. So that's 2 with an exponent of 15. So that's 32,768 times t to the power 15. So in part C, the base is negative 2 multiplied by w cubed. So that's going to be negative 2 cubed, w cubed cubed. Negative 2 cubed is negative 8. And this is going to be w 3 times 3. We often would do that step mentally. Negative 8 is w to the power 9. And in part D, we have 1 all over negative 7z all to the power 4. So that's 1 over negative 7 to the power 4, z to the power 4. 7 to the power 4 is 2,401. So that becomes 1 all over 2,401 times z to the power 4. Next is the power of quotient rules. So for any real numbers a and b, if we have a fraction a over b to the power n, that's going to give us a to the power n divided by b to the power n. So in example 8, we are asked to use the power of a quotient rule. In part A, we have a z to the power 11 all to the power 3, so that's 4 cubed all over z to the power 11 times 3. So 4 cubed is 64 all over z to the power 33. In part B, we have p divided by q cubed all to the power 6. So that gives us p to the power 6 in the numerator and q to the 3 times 6 in the denominator. So that's p to the power 6 all over q to the power 18. Part C, we have negative 1 all over t squared to the power 27. So negative 1 to the power 27 all over t squared to the power 27. That's just going to be negative 1 all over t to the 2 times 27. Now we'd often do this step mentally. Negative 1 all over t to the power 54. In part D, we have j cubed k to the minus 2 all to the power 4. So j cubed times 4, k to the negative 2 times 4. So I'm applying the power rule here. So I have j to the power 12 times k to the negative 8, and that's going to give me j to the power 12 all over k to the power 8 if I write everything with a positive exponent. In part E, we have m to the power negative 2 times n to the power negative 2 all raised to the power 3. So this will be m to the negative 2 times 3, or negative 6, times the base n to the negative 2 multiplied by 3, or negative 6. If you think about this, this is just 1 over m to the power 6 times 1 over n to the power 6, or 1 over m to the power 6, n to the power 6. Example 9 asks us to simplify exponential expressions and write the answer with positive exponents only. Part A, 6m squared n to the minus 1 all to the power 3. So that is 6 cubed m squared cubed and n to the minus 1 cubed. So 6 cubed is 216. M, 2 times 3 is 6. N to the minus 3. And with writing it with all positive exponents, 216 m to the power 6 all over n cubed. In part B, I have 17 to the power 5 times 17 to the power negative 4 times 17 to the power negative 3. So that's multiple applications of the product rule. So here I have 17, and I'll write the step in, but it's usually a mental step. So we have 5 plus minus 4, so that's minus 4 plus minus 3, and that's going to give me 17. 5 minus 7 is negative 2, so that is going to be 1 over 17 squared. 17 squared is 289, so it's 1 over 289. So the first thing I'll do is apply the quotient product rule. So I have u to the negative 1 times 2, so that'll be negative 2, v squared all over v to the negative 1 times 2, so that's negative 2. Now I have u to the negative 2, and now I'm going to apply the quotient rule. So I have v to the 2, subtract negative 2 from the denominator, so u to the negative 2, v to the power 4. Now I'll apply the negative quotient rule, so I have v to the power 4 all over u squared. Scientific notation is a way to write extremely large or extremely small numbers in a very specific way that we can express numbers in terms of the exponents or powers of 10. So the first example is, how do we write a very large number? 2,780,418. So we're going to take the decimal place. Of course, the decimal place is here, and we're going to move the decimal place left till we get 2.780418, and we're going to multiply that by 10. Well, how many decimal places did we have to move it? We had to move it from here to here, so we moved it 6 decimal places. So this is 10 to the power 6. So these are exactly the same number. This is written in scientific notation. We can also use scientific notation to represent very, very small numbers. So the radius of an electron is this tiny number here. Now, if we want to write this as 4.7 times 10 to the something, how many decimal places do we have to move this to the right? Well, we have to move it 13 places to the right. So this is negative 13. Now, another way to think about this is when you just see this number, this tells you how far to move the decimal place. If it's plus, how far to move this decimal place to the right, because this is a plus. So we know we take this decimal place and move it 6 places to the right. This is a negative here, So that tells us how far to move this decimal place to the left. So to define scientific notation, when a number is written in scientific notation, it has the form a times 10 to the power n. So a must be a positive value between 1 and 10, and n must be an integer, which means it can be positive or negative. If the exponent on n is positive, then it's a very large number. If the exponent on n is negative, it's a small number. In example A, write each number in scientific notation. For part A, it says write the distance to the Andromeda galaxy from Earth. Let me just read you this huge number. 24, and then there's 3, 6, 9, 12, 15, 18, 21 zeros following that. So that's a huge number. So to write that in scientific notation, I have to move the decimal place back 22 places. So it is 2.4 times 10 to the 22. Now let's just check that. Let's work this the other way. If I take this decimal place here, 2.4, and move it forward 22 places, so I have 2, and I'm going to move it forward. So 4, that's one decimal place, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 decimal places. Is that the same as the number I see above? And the answer is yes, it's 24, followed by 3, 6, 9, 12, 15, 18, 21 zeros. Since part B is just like A, I'm going to skip to part D. Now we have the diameter of an electron, and that's 0. Well, there's 12 zeros and then 9.4 meters, so it's very, very tiny. And what we need to do is write this. We've got to express the 9.4 as the 9.4 times 10 to the negative. We know it's a very small number. So if we had the decimal place, it's here. We'd have to move it forward 3, 6, 9, 12, 13 places. So we'll have to move it back 13 places here. And this is a very small number. Remember, positive exponents indicate very large numbers, and negative exponents indicate very, very small numbers. Now in example 11, we're going to convert from scientific notation to standard notation, and I'm going to start with part B. It's the most interesting one here, and it just says -2 times 10 to the power 6. And of course that means -2.0, doesn't it? Times 10 to the power 6. So that's going to equal -2, and then I start moving the decimal place. I have to move it forward 6 places. So that's 1, 2, 3, 4, 5, 6. And this is -2 million. Now in part C, I have 7.91 times 10 to the -7. So I know this is a small number because the exponent on 10 is negative. And I have to take this decimal place after 7 and move it back 7 places. So that's going to give me 0.000000791, and that's my very small number. Next, we'll talk about using scientific notation in applications. So, for example, if we are asked to calculate the number of atoms in 1 liter of water, we know each water molecule contains 3 atoms, H2O, 2 hydrogen and 1 oxygen. The average drop of water contains 1.32, so that's 3 times the average drop of water contains 1.32 times 10 to the 21 molecules, and 1 liter of water contains 1.22 times 10 to the 4 average drops, and this turns out to be 3 times 1.32 times 1.22, that's 4.83 times 10 to the, now we add up the powers, 21 plus 24 is 25. There's 4.83 times 10 to the 25 atoms in 1 litre of water. Now, when performing calculations with scientific notation, you want to write the answer in scientific notation as well. So in this example, we have 7 times 10 to the power 4 multiplied by 5 times 10 to the power 6, and 7 times 5 is 35 times 10 to the power 10. The problem is this is not written in scientific notation because we've got 35 and not 3.5. So the answer is not in proper scientific notation because 35 is greater than 10. Now, you've got to think to yourself here, okay, I know that 35 is equal to 3.5 times 10 to the power 1, isn't it? So then that tells me how to change my answer into scientific notation. So this will be 3.5 times 10 to the power 11 because I have to add 1 to the 10 here. In example 12, we're asked to perform the operations and write the answer in scientific notation. So for part A, I have 8.14 times 10 to the power negative 7, and I'm multiplying that by the number 6.5 times 10 to the power 10. So 8.14 times 6.5, and that'll give me 52.91 times 10. Now I've got to add the exponents on the 10. Negative 7 plus 10 is going to give me 3. But this is not in scientific notation. It's 52, and that would need to be 5.291 times 10 to the power 1. So if you wanted to think about this, and I'm going to write this intermediary step in red here, is how I'd think about this. I've got to leave it in scientific notation. So that's 5.291 times 10 to the power 1 times 10 to the power 3. And then, of course, that's my mental step. I would add the exponents on the 10. So this is 5.291 times 10 to the power 4. In part B, we have 4 times 10 to the power 5 divided by negative 1.52 times 10 to the power 9. So I'm going to start off with 4 divided by negative 1.52, and that will give me negative 2.631, and I'm just going to round off here. So instead of 5, I'm going to round that off to 6. So really I should make those the curly symbols, times, and then I have 10 to the power 5 subtract 9. So this is negative 4, and this is actually already in scientific notation. Just note that I didn't write down all the decimals here. Part D is 1.2 times 10 to the power 8, all divided by 9.6 times 10 to the power 5. So we're going to do the numerical division first. Let's divide 1.2 divided by 9.6, and that will give us 0.125 times 10, and here I have 8 subtract 5, so that's going to give me 3. Now this is not in scientific notation. I'm going to have to move the decimal place forward 1 decimal place in order to get a number between 1 and 10. So this is going to become 1.25 times 10 to the minus 1 times 10 to the power 3. So that's 1.25 times 10 squared. In example 13, we are going to apply scientific notation. In 2014, the population of the United States was about 308 million people, and the national debt was about 17,547 billion. Now we want to figure out in 2014 how much debt is that per citizen. So we write the population and in scientific notation. So that of course is 3.08 times 10 to the power 8, And the national debt in scientific notation is 1.75 times 10 to the 13. And we do this calculation and we find that it's in 2014 in scientific notation, we have about 5.7 times 10 to the 4 per person national debt, or if we're going to write it just how we normally write it, it's $57,000 per person. But I've updated this. The population of the US in 2021 is 330 million, and the national debt is almost 27 trillion. It's 2.97 trillion. So what we have here is the national debt, $2.79 times 10 to the 13. And we're going to divide that by the number of people in the US. So that's 3.3 times 10 to the 8 people. And we're going to do that calculation. Now, I'm going to round it off. It's going to have to be approximate because 2.79 divided by 3.3 is about 0.845 times 10 to the power 5. But that is not in scientific notation, is it? So I've got to move that decimal place back. So that's 8.45 times 10 to the power 4. So in 2021 now, we're at $84,500 in debt per person in the US. What a happy note to end on.